here, and we're going to pull this up. Okay, I think we are live. We've got the audio and video up and running, so welcome to Seal Design. I've been posting the videos on the YouTube channel from Blackboard here recently because I'm getting like good quality on the on my local recordings, but I'm working off of this Microsoft Surface, and boy, it overheats. It gets hot, and I think it's just from all the streaming and the live stuff we've been doing recently. I'm considering getting a Wacom One. It's basically like an extra monitor that you can write on, and just using my workstation. But I haven't quite pulled the trigger on that yet, but we'll see. Okay, your homeworks to date have been graded, and today, before we jump into design, it might seem a bit repetitive, but I want to do another tension member analysis problem. This problem has some quirks and challenges that are new that we haven't dealt with yet. They're handleable. Like, we have all of the tools necessary to handle this problem, and I've got a homework assignment coming up that's going to be very similar to this. Now, I'll go ahead and tell you that I haven't created the assignment yet. I'll probably get that uploaded like at around 1 or so, because you'll see I'm making it a bit custom. I'm doing something a little different. Somebody raise their hand?
Yeah, can you hear me, Dr. Michelson?
I can, yes. Can you hear me?
Yes. I had a question about the homework.
Sure, yeah.
The current homework that we just turned in. So I believe it was the FU, and you had an upper bound and a lower bound. It was like 58 to 80. And I was just curious as to how do we know which one to use? I mean, if you used either value, you still got the same result. You know, the yield stress was still higher or still lower, so it was the control factor. But I was just curious as to which one we know to use.
So I'm going to turn that around to the class. Anybody know which one to use whenever you have a range?
Always the lower one.
You always use the lowest value. That's correct, because the reason that the range is presented is because certain steels, certain grades of steel can actually have a range of FU values. The reason for the range is because higher strength means lower ductility. So you as an engineer need to be aware of that in some scenarios where ductility matters, like in earthquake land. But in general, whenever you have a range, use the lowest. Now, you're also bringing up another point, that is that for that problem, it didn't matter, because when you went and did the gross section yielding check and the net section fracture check, you found that gross section yielding ended up governing. The point I'm making there is that's why we check both, right? There are 2 limit states. There's actually going to be 3 limit states later on in about a week or so, and you check them all, and whichever one is the controlling one is the one that governs your design. Sometimes it's net section fracture, sometimes it's gross section yielding, and it just depends on the connection. Like, if we talk about that homework problem, what if I used bigger bolts? Well, that would mean an increased hole diameter, which would mean a lower net area, right? So, or what if I arranged the bolts in a different fashion? That can mean a lower net area such that that limit state governs. So that's why you have to check both. Now, there was another hand raised. I think that was Mr. Adkins. Did you have a question?
I was looking in the steel manual here. It was related to the 80 KSI part of the tensile stress.
Yeah, I'm going to pull my steel manual up right here. Go ahead.
According to the manual, for wide flanging shapes with flange thickness over 3 inches, only the minimum of 58 KSI applies. So, in this case of the tensile stress, we should stick with 58 no matter what. Unless...
Well, I mean, I see what you're saying, and the reason that you're saying that is because, or the reason that the manual says it, not that you're saying that, the reason that the manual says that is and I mean, you can even look in table 2-5, you can get different behaviors of string vary based on its thickness. As plates get really, really thick, sometimes the ultimate tensile stress and whatnot is capped just by the metal structure that you get from a plate that thick. Like if you look at the structure of the atoms and whatnot. But regardless of that note, there is a range. And I mean, I guess as the engineer, you could use whatever value you want. I'm saying that to use common sense practical engineering, always use the lowest value. Don't ever go with an average or a high value on that. All right. Any other questions? All right. So today, first off, let me recap a couple of things to make sure that we're all on the same page. So we're still going through with the idea of LRFD limit states. We're still utilizing this concept that we have, factored loads and factored resistances, and hopefully that was clear. And after not just the example that we did yesterday, but the homework assignment, this concept of using factored loads and factored resistances, we will be doing all semester. I mean, like 1.2 dead plus 1.6 live, we'll be using it all semester. A nominal resistance times a phi value, using it all semester. The formulas for nominal resistance might change. The individual values we use for phi might change. Sometimes we'll use 0.9. Sometimes we'll use 0.75. There might be there's an instance with slip where we can use 1 as or shear yielding where we can use 1 for phi, and it just depends on the particular limit state that we're looking at and the mechanics associated. But the idea is that we take our nominal loads and increase them by load factors, and our nominal resistances and decrease them by resistance factors. And as long as the factored resistances are bigger than the factored loads at the end of the day, we're good to go. We have our LRFD load combos, which by observation, you will probably find that in most instances, you'll end up using either 1 and 2 for most main member design. And the reason why is, by design, or I don't want to keep throwing out that word, just by default, that's probably a better word. By default, just about every member in a structure experiences 2 loads, a dead load and a live load. The dead load because it has to hold up its own self-weight, and the live load because all structures are designed to hold something up. Like, if I'm designing a school, it has to hold up the loads associated with the school, or same thing with a library or a fire station or whatever. So by its nature, dead load and live load are going to be very common. And as we said before, not every element in a structure experiences snow load. Like the floor beams in my office don't experience any snow load or wind load or whatnot, but some elements do. But just about everything experiences dead and live. For the tension member, we have so far 2 limit states: gross section yielding and net section fracture. The gross section yielding capacity, the factored capacity, is computed as FYAG times the resistance factor of 0.9 for net section fracture. It's FU times AN times the shear lag factor, adjusted then by a resistance factor of 0.75. And again, the lower of those 2 values is what's taken to govern. For our steel values, and this goes to Mr. Roman's question, we can find the FY and the FU properties for a given steel grade either on table 2-4, table 2-5. Whenever you have a range, always use the lower value because it's more conservative. For our expression for AN, and this is what we're going to kind of use today, and this is kind of, again, going to be the star of the show. For bolted connections, if we want to find the net area, we take the gross area minus the area lost due to bolt holes, so the diameter of the hole times the thickness, the diameter being the bolt diameter plus 1/8 of an inch. And then we add any necessary stagger factors. And there's going to be some quirks with that today. Shear lag factors, and that's another thing we're going to, like, this actually really isn't going to be a factor today, and that'll become clear as we get into the example. Just one thing, make sure that you are reading the table, make sure that you are reading the descriptions, and that you are applying the descriptions to the problem in question. For example, I had a few questions from some students that said, well, how do we compute X bar for the channel? As we dug into it, what it was is they were trying to turn the channel into an equivalent WT, but that equivalent WT issue is only for W sections connected via the flanges. The homework was a channel, so you didn't need to do that. And if you go to the example that we did in class on Monday, we actually did U calculations for a channel connected by the web, so you could just go off of that process. So just make sure that you're not just, you know, blanketly repeating everything we do in a particular example, that, you know, you're reading the case and applying the case that applies to the problem in question. Okay, and so this is going to be our problem for today. And I want to illustrate what's going on here because it might be a little confusing. So we have an angle, okay, so this is an L shape that has two lines of bolts in one leg and one line of bolts in another, okay? But we kind of need to look at this three-dimensionally, and it's a little hard to see probably with the way it's kind of drawn here. So I got a little fancy. I'm going to pull this up here in a second. So this is going to be A36 steel, but I got a little fancy. Let me hit escape here. And I got Inventor loaded up. Okay, so this is Inventor. And so Inventor is basically AutoCAD for mechanical engineers, I guess would kind of be the best way of describing it, but you can use it to render parts in 3 dimensions. And so I tinker around with it every now and then in steel design if I'm trying to illustrate something. And here with the class being operated virtually, I thought this would be kind of a good thing to break out. So this morning I sort of drew this part in 3 dimensions. And so this is kind of what you got going on. Let me zoom in over to the connection. Let me see if I can zoom in here. So what makes this complicated is the fact that the stagger is now crossing over from one element of the cross section to another, right? So how are we going to compute the stagger factor? So like we can do this. Let me try something here because my screen's flashing a bit. Let me stop share, or actually let me share my screen. I want to see if that reduces the flashing a bit. Okay, I think that worked a bit. Okay, so how are we going to compute the stagger factor? That's going to be kind of tough, right? Because over here, you know, we've got this this sort of, you know, I think it's going to be okay to do this part, but how do we compute the stagger factor there? Because if I orbit, you can kind of see like, okay, there is going to be a diagonal component there, right? So it's all about how do we do that. And so the way that we're going to do that, let me show you how we're going to do that. So can everybody see the board over here? Oh, I think my live stream froze on me a bit, but that's okay. If my camera decides to be funky on me, I can just pull my notebook up. I'll just pull the notebook up. All right, I also changed this example up a bit, so let me bear with me for a sec. I'm gonna screen cap this and put this in the slide. Okay, that's a little better. Okay, so the way that we're going to handle this is we're going to try and turn this angle into an equivalent plate. Okay, and so let me explain how we'll do that. All right, let me go to view. Let's go to draw and view full screen. Okay, and so hopefully this will kind of explain this little image here on the right, because I'm sure you're seeing this, you're like, I don't understand what's going on there. Okay, so we have here an angle. All right, and I drew it sort of off, like I guess that's a little off scale. Let me redraw that, try and make sure those legs are the same, because they're both L 5 by 5 by half. Okay, now I have a bolt hole here, and This dimension we know is 3 inches. You know, that's 3 inches right there. And then we have another bolt hole, and I'm only going to focus on this first one up here, and you'll see why, where that dimension is 2 inches. Okay. Now, first off, is everybody like clear with the, I guess, sort of the challenge that we're going to have to address? The idea that that we've got a stagger that crosses over a from one leg to another. Everybody clear on that and the challenge that we've got associated? I'm assuming everybody's okay with that. If you've got any questions there, let me know. All right. So let me explain how we're gonna address this. Okay. Now I want the chat to help me out with this. What is this dimension right there? Keep in mind that maybe I'll scroll up a bit. Keep in mind that this is an L 5 by 5 1/2. It's 2.5 inches. Oh, I had a typo here. I forgot to include that these are 3/4 inch diameter bolts. So I'll have to update my slides on that. But yeah, these are 3/4 inch diameter bolts. But you're correct. This is 2.5 inches. This is 2.5 inches. Okay. So let me explain what I'm going to do in order to account for this diagonal path. Okay, and I'm going to draw this angle again so it doesn't get too cluttered. So here's the angle. What I'm going to do is I'm going to use my age-old weapon of the samurai sword and a lightsaber, and I'm going to recognize that if I cut this, I'm going to cut it into sort of 2 pieces. Okay. The first piece I'm going to recognize is sort of this, like maybe this part, right? And then the second piece, maybe we'll say the second piece is that part, right? Okay. And then what I'm going to do is I'm going to take that red part and I'm going to stick it on top of the green part, right? So I'm actually going to move this. I'm going to sort of rotate that over like that so that when it's all said and done, I've got a single plate that's sort of super long, right? And so I'm doing that because I've got this stagger that crosses over a leg. And so I want to be able to do that so I can figure out what's the stagger factor going to be for that leg. Does that make sense? I want to take, we're going to do all the math with the dimensions and we'll figure out the dimensions and all that stuff here in a bit. I just want to make sure that the concept makes sense. Okay. And if anybody has any questions, let me know. We're unfolding the angle, basically, you know. All right. Now, so what we're going to have is we're going to have a big old plate at the end of the day. Okay. And we're going to have sort of this like imaginary dashed line. This sort of goes like that. And that dashed line basically refers to that piece right there. That's where I've cut the angle apart and I've folded it up. So let's see if you all are paying attention, okay? And I'll put a little break line here. All right. So help me out. How long is that? Let's see if y'all are paying attention. How long is that?
Is it 5 inches?
No. Here, I'll tell you. That is 5 inches. it's 4.5 inches. Because what I did, so what we're talking about, so that we can understand the context, we're talking about that dimension, right? Because that's the dimension right here. I'm trying to use my colors to sort of indicate the dimensions here, right? So that dimension right there is 5 inches. This is 5 inches. So that's 5 inches. But the 4.5, the reason why it's 4.5 is because if we made that 5 too, we'd be double counting the thickness, right? So the total height of the plate has got to be 5 plus 5, but we got to take off 1 thickness, right? Does that make sense? And I'm going to take my time on this. I want to make sure that it's clear. I don't want to barrel through this. I'm going to try something here. Give me 1 second. If I can calm down my computer a bit. Maybe if I turn off my camera, that'll help. Okay. Is everybody with me? Everybody's being kind of quiet today, so I mean, I'm not really hearing much. I want to make sure that y'all are clear on this. Don't hesitate if you got a question. If we are subtracting the thickness, well, the thickness is a half because it's an L5 by 5 by 1/2. Yeah, yeah. So this angle down here is an L5 by 5 by 1/2 inches. Everybody good? I mean, again, don't hesitate. Okay. All right. Now, let's see if I can transpose these bolt holes down here. So I've got a bolt hole like that, like that, and like that, like that, like that, and that, that, and that. Okay. And again, all I'm doing here, and I'm going to use my inventor here again to make sure that everybody's clear on this. So again, all I'm doing is I'm cutting that there, sticking it on the plates. That's why I have like 3, 2, and 3. Like this is the example that we're looking at. Okay. So just to make sure that everybody understands the context. Okay. Now, we know from the drawing up here that all of these horizontal spacings, if you look at this dimension right here, we know that they're all 1.5 inches in that way. So let's make sure everybody's paying attention. That 1.5 inches, is that going to be an S value or a G value? And just to be clear, we're yanking on it this way. That's the way we're yanking on it. That's the S value, right? So with all of these, we know that this, all of these are 1.5 inches. I know my drawing isn't perfect, but that's close enough. And so really, if we want to look at this from a net area perspective, what we need is this dimension and we need that dimension, right? Now this one we know, right? That one we know. We can get that from the schematic up here because that's going to be what, right? What is that dimension? That's this, right? The distance between those two bolt holes is 1.5 inches, right? So that makes this 1.5 inches, right? That's easy. So the others we got to figure out is you know this central one right there. Okay. Everybody with me so far? Okay. Now, good. Okay. We know, let's sort of focus on, let's see, let's focus on this. Oh, sorry, meant to do my highlighter. Let's focus on that for a second. And let's focus on this. Okay. We know that from this hole to the top of the angle, we know that's 2 inches. Okay. So if you look at the way that we split our angle up, because see, we split it up like this, right? We know that top or that bottom dimension is going to be 2 inches. This value is 2 inches, right? From that top hole to there. So if that's 2 inches, is this 3 inches or is it something else? Again, my art could have been a little better. 3 inches minus the thickness, exactly right. So this is 2.5 inches, which makes this 4.5 inches. So the overall point I'm making is that when we compute the net area, there are 2 different cases that we're going to have to consider. There is a case like this, which is just going to be the gross area minus 2 bolt holes. But then there is going to be a second case that looks like that. Okay. And so in that case, we're going to have the gross area minus 3 bolt holes plus 2 stagger factors. But those 2 stagger factors are not going to be the same. They are going to be different. And they're going to be different because they have different gauge distances. That's what makes this problem a little challenging. If you understand that, then the rest is really going to be very plug and chug. It's going to be very simple, actually. I'll break up my calculator to work it with you. Any questions? Because we're going to start knocking this sucker out. Keep in mind that the purpose of this problem is a bit more contained. We're not trying to do a full-blown analysis problem like we did in the last problem. Here, we're just trying to determine the design axial capacity. So I just want to know what is phi PN. I just want to know what the tensile capacity is. All right, so let's see if we can start knocking this thing out. Okay, so first off, we need to know some properties of A36 steel. Now we're going to look these up in table 2-4, and I need to know what FY and FU are. Now I'm going to start calling on some people because y'all been a little quiet today. So FY is 36 and FU at 36, but it's not 36, it's 36 KSI. And then FU is what? Now come on, somebody else. I'm going to start calling on people. There we go. All right. 58 KSI. Here, I'll make sure that's not super squunched. Now, the next thing, we're going to need some properties for the shape. And so this is an L 5 by 5 by 1/2. And so let me put a reference there. That's going to be in table 1-7. And so we're going to need a gross area for this. And we're going to need, now we're going to need a thickness, but we know the thickness. That's just a 1/2 inch. What's the gross area? Okay, 4.79 square inches. All right. If the lower bound for FU we wouldn't use it for axial design. The recognition of the upper bound is more for ductility concerns that happen in earthquake land. Because in earthquake land, you're putting the structure through a very large degree of lateral translation. It's undergoing a lot of deformation. And so understanding the ductility in earthquake land is very important. But to be clear, earthquake engineering is kind of a whole nother animal in and of itself. Just the way that you approach it, the way that you handle it. I mean, we're on the ground floor of structural engineering with what we're doing here. This is like really advanced stuff in earthquake land. So yeah, I don't want to like gloss over the answer and say, oh, don't worry about it. But how you classify a structure, what your R values are, what your overstrength factors are, and all that, there's some discussion to be had. I might talk about that near the end of the semester, but it's stories for another day, I'll say. Okay, so with any tension member problem, if all you're considering is gross section yielding, net section fracture, the two challenges are to compute the net area and to compute the shear lag factor. If you get that, you got everything else. So let's start off with the net area. Now we have a bolt diameter that is 3/4 of an inch. So to make sure everybody in the class has a pulse and a respiratory pattern, somebody else tell me, if the bolt diameter is 3/4 of an inch, what is the effective hole diameter?
Unless it has changed to 7/8 of an inch.
That is absolutely correct. All right. So if we go back up to our, handy dandy sketch here, forgive me, I have a 2-year-old, so I've been watching a lot of Blue's Clues here recently. So if I said handy dandy sketch there, handy dandy notebook. All right. So we have our
one.
The new one, I guess.
It's a reboot of the original.
The guy's name is Josh, so I'm guessing it looks new. It looks new. Yeah. So the episodes get stuck in your head more than you think. Okay. So we have two different paths to consider. So what I'll do is, just for the sake of discussion, Steve is the OG. Okay, you're right. Yeah, I remember. Yeah. So this isn't Steve. This is Josh. Yeah. All right. So we'll call this path 1, and we'll call this path 2. Path 1 and path 2. So path 1 is going to be just the gross area minus 2 bolt holes, and then path 2 is going to be the gross area minus 3 bolt holes, but I'm going to add 2 stagger factors, and those stagger factors are going to be different. So let's see if we can reason through this. So net area 1 is going to be the gross area minus 2 bolt holes. So the gross area minus 2 times 7/8 of an inch times 1/2 inch. And so, I should have plugged the number in there. That would have helped. So the gross area, we just looked that up. That's 4.79. And so what do we got for our first net area? Let me rewrite that because that's kind of squunched. It's going to bug me if I don't do that. Okay, that's what I got. All right, so that is 3.92. And then, okay, so our second formula, maybe I'll actually, maybe let me do this. I'm going to cheat here a bit. I'm going to drag this down, sort of move this down here. Because our second formula is going to be a little bit more involved, right? Because our second formula, we're going to take the gross area. We're going to subtract 3 bolt holes, but we're going to add 2 stagger factors, but they're different, right? Each stagger, it's not just, you know, computing a single stagger factor and then, you know, doubling it. The stagger factors are different because we have different G values. And so this is going to be a little bit more involved. So we have 4.79 minus 3 times 7/8 times a half plus, and then we've got, okay, so now let's see if we can reason through this. What's our S value again? I think it was Mr. Enoch that pointed that out. What was our S value?
1 1/2 inch.
1 1/2 inches. Okay, and that's squared times a 1/2 inch over 4. And then, okay, now I'm going to have to scroll up for this because we got a G1 and a G2. So one of them is 4 1/2 inches and the other is 1 1/2 inches. So 4 times 4.5 inches plus 1.5 inches squared times a 1/2 inch. And then 4 times 1.5 inches.
Can you just briefly discuss how we understand how the S and the G's are? I kind of remember, but I'm not like 100% sure.
That's completely fair. Okay, so whenever you have a tension member, right? Okay, and I'll just sort of like draw some holes like that, you know, and you know, here's the tension member, and you're yanking on it like this. Okay, whenever you're yanking on it, the S values are parallel to the load, and the G values are perpendicular to the load. So, you know, if you were yanking on it, you know, if you had a tension member like this, and, you know, you had, I don't know, something like that, and you were yanking on it, then this would be S, and that would be G. Yeah, that's a fair question. All right. All right, so let me lay out my system parameters. And then my starting equations. I'm sorry. I couldn't help it. All right, somebody got an answer for me? While you do it, I'm doing it as well, because I made this problem up today, so I had a little bit of fun with it. All right, anybody got an answer for me? You're verifying my calcs today. Y'all are unusually quiet today. All right, so 3.7, we'll call it 7.3. There we go. Okay. All right, so of these, so we've got a value here and a value here. Which one are we going to take? There we go. We always take the lowest, right? Because this is a resistance. So AN is 3.73 square inches. Okay. All right. Now, remember I said that the two challenges really with tension member analysis, if you're not considering slenderness or whatnot, are the net area and the shear lag factor. Now, before we get into that, so first off, the shear lag factor is in table D3.1, and remember, the trick is to always read the cases, okay? Now, I'm going to share my screen. So remember, this is the table that has the cases. And to go on with our theme, okay, that was pretty bad. Let me try it again. Does anybody see that? I think it's a clue. All right. Now, if you read case 1, remember when we first started looking at tension members, we said that if you look at the table, there's 8 different cases, but really the ones that dictate what's going on are either case 1 or case 2. Like it all spurns from case 1 or case 2. Case 2, the 1 minus x bar over L, that is when some of the cross-sectional elements are connected by fasteners or welds. Case 1 is when they're all connected by fasteners or welds, right? This is an angle. An angle is comprised of 2 legs. Both of those legs are connected. What's the deal here? The deal is that U is 1. Let me pull my notebook back up. A handy dandy notebook. So U is U1, case 1. Now there you go. That's the question you want to be asking. Okay. So, all right. Case 2 would be the one that applies. Case 2 would be applied when only one of the legs were connected. But you could also look at case 8 as well. But in this instance, because all of the cross-sectional elements are connected, we can go ahead and take case 1 to be the one that applies. If it was only one leg, case 2. Because case 2 applies when only some of the cross-sectional elements apply. So really, it's case 1 and case 2 are really the ideal ones that you're going to want to refer to first. So now what we can do is we can assess our limit states. So gross section yielding says that PPN is 0.9 FY AG. And then AG, what was AG again? I think it was 4.79. And then for net section fracture, and then net area what was in that area? 3.73 times 1. And so yielding we got 155.2. And then 162.3. For fracture. So yeah, it seems cruel that after all that unfolding of plates and weird stagger factors, that in the end it didn't govern, because which is the one that matters? That's the one that matters. Whenever you're assessing multiple limit states, what's the capacity? The capacity is the one or the limit state that yields the lowest value. So between 155 kips and 162 kips, if I'm yanking on that member, what am I going to hit first? I'm going to hit 155. Therefore, our design strength is 155.2 kips. Boom.
If we're doing slenderness, the R value recorded in the book's always the R minimum, right?
Yes, that is correct. And so all right. So for an angle, whenever you're looking at an angle, there will be 3 R values listed. There will be an RX, an RY, but then there's an RZ. The reason for the RZ is because angles do not possess an axis of symmetry with respect to the X or the Y axis. So like if it's an angle and the legs are equal, the axis of symmetry is at a 45-degree angle. If it's unequal, there isn't an axis of symmetry at all. So the RZ is always going to be the minimum for an angle. And you can look at RZ values. You can kind of see if the legs are equal, there's this alpha value, this tangent of alpha. The tangent of alpha is always 1. Whenever the legs are unequal, the tangent of alpha is like, there's a value to it. And that's just the angle of that principal axis. Okay, somebody raised their hand. Let me see who that was. Mr. Enoch. Yes, sir.
Can you go over again how you knew exactly what path it was going to take instead of having to draw out all the different possibilities when we were talking about the fracture?
You talking about this? I want to make sure I know what you're talking about.
Yes. So in that case, whatever line you take has to go through both bolts, not just one, on the lead line.
Well, the lead line. So let me. I think the easiest way to answer that might actually be to pull up Inventor. So, give me a sec. Hold on. Okay, so here's the tension member, right? And so if I sort of pull it like this, okay, so I think you could probably see the compass. I'm going to use the compass as kind of like a laser pointer. So this is the gross section all the way out here, okay, and the net section is going to be, somewhere, in this vicinity. So the first thing you got to do is you got to identify the lead line of bolts. So the lead line of bolts are all the all of these bolts here, those 3, the ones that are closest to the gross section of the body. And then, again, what you have to do is you have to just draw all of the possible failure paths that leave those bolts intact. So it wasn't me, like I didn't look at it and just sort of, well, it's going to be this and this. It's like you have to look at the connection and identify all of the possible ones that keep those bolts intact. Now, if I had just drawn like a single path that goes like that, I mean, yeah, sure, this bolt is on the lead line, this one here, but if I were to fail that, like, imagine samurai sorting through, that path right there, and I yank the member. Well, not only am I separating the member, but I got to shear these 2 bolts in front, and that would sort of violate the rules that we've conditioned. So all the failure paths are going to be the ones that follow this lead line that leaves the bolts intact. And so for this connection, that was really only 2 paths. That was, You know, just this straight perpendicular path in front of these two and the zigzag like that. Did that answer it? I mean,
It did. It did. I think I was a little bit confused because, you know, in the homeworks that we've done, there were a few more bolts, so maybe there was a little bit uncertainty as to what exactly line it was going to take. But whereas this only has like a total of like 8 bolts in the entire member, then, you know, it would make sense that you could get it more quickly.
and there's only 3 of them that are on the lead line, and you know, I think it was our first, or it might have been homework 2.2, I think it was. That connection had a lot of bolts, and not just a lot of bolts, but a lot of bolts on the lead line. So there were all sorts of different diagonal paths that you could consider. Whereas this one, there just aren't that many. All right. Any questions before we call it for the week? All right. Real quick, I just want to remind you, so give me about an hour. I just hadn't gotten around to finishing the definition of the homework assignment, but it'll be up. You need it today. Oh, the lecture. I thought it was good to do this again because this is so important to what we do just throughout the semester, that just the fundamental concept of comparing load and resistance, of going through this stuff again. I don't want you to get lost in the details. I want to make sure that you're understanding the big picture. But yeah, real quick on the housekeeping. Give me about an hour or so to get the final or the homework assignment up. I will post on Teams when it is available on Blackboard. And until then, I will see you all on Monday. And Monday, we're going to start some design. We're actually going to start tension member design on Monday. So hopefully you'll get a kick out of that. But it's pretty straightforward. That's all I have, everybody. I'm going to stop the recording. And I will see you all next week. You all have a wonderful weekend. We'll see you then.